Today's video is on reduction and oxidation, or redox put together, reactions. And we're assigning oxidation numbers. We're looking at oxidation half reactions and then reduction half reactions, and we're learning how to balance simpler redox reactions. Now, there are more complex redox reactions that can be balanced, but we're not going to learn it in this video. We're just learning simpler redox reactions. If you look at this class, this might be one to take some good notes on. This is some rules for assigning oxidation numbers. So what is an oxidation number? Oxidation number has been something that you've seen before in charges. We oftentimes see those oxidation numbers as charges as well. But not all substances are ionically bonded, so we have oxidation numbers for covalent compounds too. And so what it means, the definition that I've seen over many textbooks, the best definition is valence electrons involved in bonding. So oxidation numbers are all the valence electrons that are involved in bonding. Sometimes you're going to need to go back to this definition to use it as a guideline for determining oxidation numbers. So here's the set of 4 rules that I go by. I usually follow it in this order here. I assign oxidation numbers to one atom of a given element only. When I assign the oxidation numbers, I usually do it to the anion first. You'll see me go to the anion first, and then sometimes I go to group 1 and group 2, because group 1 and group 2, which are your alkali metals and your alkali earth metals, they don't usually change in oxidation numbers. They tend to have the same oxidation number. Group 1 usually has a +1. Group 2 usually has a +2. Now, when we assign oxidation numbers, I then do the cation afterwards. And the reason why I do cations last is because cations oftentimes take on multiple oxidation numbers, especially your metal cations. More electronegative atom has a negative oxidation number. That's usually a guideline that I keep with at all times. The more electronegative, the more negative. And that's why your anions, usually being the more electronegative, because it has higher Zeft and less shielding, tends to have the negative oxidation numbers. Okay, let's do some example problems with assigning oxidation numbers. So again, I follow that same guideline. I go with my anion first, F. F usually has a -1 oxidation number, so I put a -1 as my oxidation number. Now, in light of that, there's 6 of them, so what must U be? It must be positive and +6 in order to neutralize and have a charge, an overall charge of 0. Again, you'll hear me use the word charge in light of oxidation numbers oftentimes because it does represent charge. But again, not all compounds are ionic compounds that have charges. Some of them are covalent. So let's look at this next one. I do my anion, which is oxygen. Oxygen's -2. And again, I'm doing a lot of algebra along the way as I go through my oxidation numbers. Now, hydrogen, I know this is an acid. So acid, hydrogen is +1. Sulfur. Now, sulfur, they all have to add up inevitably to a net charge of 0. So if I have 2 positives, I have sulfur being something that I don't know at this point. And then oxygen is negative, and there's 4 of them, so times it by 4. Charge-wise, I get -8 here. I get +2 here. So what must sulfur, that one sulfur atom, be in order to have a net charge of 0? Well, it's got to be +6. So that's the oxidation number of sulfur. We go over here, this is chlorate ion. It has an overall charge here of -1, so we've got to watch out for that. Oxygen is -2 times 3, so times it by 3 gives you -6, plus what gives you -1, so it's +5. Add these two, you get -1. Here I have an alkali metal. I know it's right off the bat, it's a ionic salt, and so I know off the bat that this metal has a +1. Oxygen, once again, -2. So I could interchangeably do my alkali metals first if I wanted to. And then I do oxygen, and then chromate. Once again, I do my math, times this by 2, times this by 4. This gives me a -8. This gives me a +2. What added together with chromium gives you a net charge, or a net charge of 0. And that ends up being a +6. Now, you got to be careful with this one. This is not your typical oxygen. This is actually called peroxide. Peroxide looks like this. What must each oxygen be in order to have a -2 charge, or for 2 of them to have a -1 or a -2? It must be -1 each. And hydrogen here is +1. Ammonia. I'm going to draw ammonia just really quickly so you can see the electrons that are involved in bonding. So this is ammonium ion with a +1 charge on the nitrogen. So it looks like it's lost an electron from another ion that's gained it, an anion that's gained it. So if you look at this, how many electrons are involved in bonding? 1, 2, 3, 4, and then the one that lost its electron. So there's 5 electrons that are involved in bonding. So this is +5, and then this must be -1. So this is a -1 oxidation number. Once again, this is a covalent compound, so it's kind of, you do have to stick by the definition that it's all the electrons that are involved in bonding. And nitrogen tends to be more, so I'll leave it as that in terms of the oxidation numbers, okay? So 1, 2, 3, 4, 5. 5, the 5th one being the +1 charge, okay? Now, why is this important? Well, most of your reactions are actually redox reactions. And redox reactions, most of the reactions in the world are redox reactions. So you'll come across a lot of reactions that you're familiar with, thinking that it's a single replacement reaction or a combustion reaction, when in fact it actually, rudimentary wise, is a redox reaction. So I like to use this little mnemonic. It stands for certain things. So Leo says GR. So lose electrons means oxidation.